Hi, I'm Tristan Tomlin from the Technical University of Eindhoven. I'll be presenting the paper on a new generalization benchmark on level difficulty in reinforcement learning. This is a joint work with Jianhong Dai from Imperial College London and Meng Fang and Mikola Pechinitsky from TU Eindhoven as well. One of the typical ways we use reinforcement learning is in which we aspire an agent to reach some objective and in a given environment. And in order to achieve this, we often apply some learning method, like a policy gradient, and if all goes well, we achieve the desired result. Now, it would of course also be nice for this trained AI agent to be able to thrive in unencountered situations. But if we naively try to do so, we're quickly to realize that this results to being very untrivial. So in order to cultivate generalizability in AI, we first need proper research platforms and benchmarks to develop and evaluate these methods of doing so. So a good way to go about this is to use video games, as they act as a suitable ready-made simulation environments which are virtually observable. Further, they provide complex problems for the agents to solve in a very safe and controllable setting. Further, they imitate this canonical reinforcement learning loop in which you have an agent perform actions within the environment and immediately receiving reward from it and the new observations. And last, the since the primary observation of most video games is visual, which demands that the agent learns from pixels, this enables us to visually modify the environment with human knowledge, and the more we do so, the greater of a challenge it should present the agent. So if we take a step back and look at how humans learn new and complex tasks, then it generally starts by starting out with easy ones, practicing easy ones and accomplishing those. And once the human has sort of built a certain skill set, they can then generalize from that to be able to accomplish more complex and newer tasks. So it may be meaningful to evaluate AI generalizability in a similar fashion by training it in a set of easier environments and evaluating it on more complex ones. So I'll shortly describe what some previous works have attempted to do in resolving this. So first we have Obstacle Tower, which which sort of introduces a very uh, complex environment with up to 100 levels of difficulty, of increasing difficulty, in which the agent has to solve puzzles or evade obstacles or even kill enemies. But this environment has the third-person perspective, which sort of loses out on this embodied nature, which is often very crucial for real-life applicability of robotic systems, for instance. Further, we have Maze Explorer, which is based on the legendary old FPS game Doom, but it only targets navigation and exploration, and it does so by modifying only the layout of the environment and also the textures. Last, we have CRL Maze, which is essentially designed for continual reinforcement learning. It's also based on Doom, and it designs this object picking task for the agent, in which it has to navigate in the maze-like environment and evade certain items and pick up other ones. And what they do is, at given points in time, they modify the environment by dimming the lights or swapping out the objects. But as I said, this is not focused on generalization, but more on continual RL. So essentially, there's a certain, among the works described and some other ones, there's a certain lack of benchmarks with difficulty levels specifically tailored for generalization. So to this end, we present the LevDoom benchmark, which is established in a semi-realistic 3D environment based on the game Doom, in which the agent is embodied, meaning it perceives the world in a first-person point of view, being able to navigate and interact with the world around it. And the benchmark consists of 4 scenarios, each uh, also consisting of modified environments. Uh, the first of the scenarios is defend the center, in which the agent is positioned in the center of the circular room and it's given a limited amount of ammunition to fend off encroaching enemies who wish to inflict damage. In the second one, the agent is trapped in an environment of which the surface constantly inflicts damage to the agent, and the only way to survive is by moving around and collecting these health items. And the third one, the agent is in a maze-like environment and has to navigate around by finding enemies and eliminating the enemies. And the last one, the agent is positioned at one end of a rectangular room and is only able to move laterally. So what it has to do is evade these incoming projectiles from the enemies across the other end of the room. And further, we differentiate between levels of difficulty within a scenario of these environments. So what are the ways that we modified these environments? So the first thing we can do is change the textures, which creates the sort of different visual pattern on the surrounding floors and walls, which have the tendency to confuse the agent. Further, we could change the in-game entities or the objects or enemies, giving them a new appearance and a new behavior. Then we could resize them, giving them a different shapes and size. Further, we could create obstacles, which would obviously impede the movement of the agent, but not only that, they might act as potential relevant targets for the agent. So it might try to shoot them or try to pick them up and confuse it for something else. We could change the rendering of these items and objects, which would render them transparent and being more difficult to detect. And finally, we could vary the height of the agent, which would shift the field of view. Right, so how does all this define difficulty? So the way we do this is by combining uh, the modifications. So as you can see, for each, so this is the table with all of the environments of the defend the center scenario, with each environment with its modifications and the difficulty level. So each scenario has a sort of base environment, which we call the default environment. And if we add a single modification to that, we end up with the level 1 environment. And if we combine them, then the level increases. The only exception is level 4, in which you can see that all of the possible modifications are present. What we noticed was that adding 4 or more modifications didn't really make much of a difference. So we decided to omit the intermediary levels and only keep one last final level with all of the modifications. So I'll talk about what the default intended use of the benchmark is. So the agent ought to be trained in a multitask setting on all of the lower level environments, 0 and 1, of a single scenario, and then evaluated thereafter on the same scenario on the higher levels, 2, 3, and 4, on all environments. And the way we measure success of the agent in the 3 scenarios of defend the center, health gathering, and dodge projectiles is by counting the number of frames the agent managed to survive, or when the episode terminates. And for the last scenario, we simply tally the number of kills it is able to achieve. So further, we evaluate some popular vanilla reinforcement learning algorithms as baselines following this very same protocol. So what we do is train each agent for 10 million iterations using multiple seeds and evaluate the agent after every 100,000 steps for 30 episodes. So looking at the results, we could see that the agent still managed to generalize to level 2 tasks to some extent, but combining 3 modifications already causes the performance to measurably decrease and further completely diminish in the final level. So if we look at the more quantitative results, we can see that if we compare the algorithms to one another, we can see that Rainbow outperformed the others in the first 3 scenarios and PPO did so in the last one. What we can notice is that within the Seek and Slay scenario, the third one, PPO had a very poor performance. We hypothesize that this is due to the on-policy nature of the algorithm, due to it having no replay buffer and thus being rather unstable at times. So now if we aggregate the results according to the difficulty levels, we can see the sort of clear pattern of this distinction between the levels according to the results. So this is essentially what we want to see because it sort of verifies that sort of validates this level design, that it presents the agent with an increasing complexity. So I'll address a few limitations that the benchmark has, also mixed with some potential future opportunities for work. So first of all, there's really no guarantee that individual modifications present an equal challenge. Whether it's important or not is not sure. So for instance, most of the modifications are only visual, but some also affect the game dynamics, like changing enemies or adding obstacles. So this means that environments from the same level with a different combination of these modifications might not have the same complexity. So for more consistency, in terms of results, it's always wiser to just use all of the environments suggested. So the results average out and follow this trend that we saw on the last slide. Further, the 4 scenarios we designed address only a few competencies of the agent. So adding further scenarios would make it also able to address other competencies like memory, spatial reasoning, or multi-agent collaboration. And last, for simplicity and ease of training, we restricted the action spaces of the scenarios, mainly only keeping the actions that were really crucial for accomplishing the established objective. But Doom is, of course, a bit more of a complex game in terms of the possible actions that could be taken. So employing full action space would thus enable cross-scenario experiments, but it will also require some of the scenarios to be modified in that regard. So to sum it all up, we presented a benchmark for assessing AI generalization on visually modified environments with levels of difficulty. And further, our baseline algorithms that we used failed to successfully generalize to the higher level tasks. And if you're interested, you can check out the code following the link down below. And that would be all from me now. So I hope you found it interesting, and I wish you a pleasant rest of the day.